Mr. President, Mr. Chancellor, purpose of this lecture is to try and convince you that complexity exists at the fundamental level of our knowledge. Next. Now. Let me start with the first remark. Vada. Avanti. First remark. Go on. People speak of complexity as a source of new insights in physics, biology, geology, cosmology, social sciences, and in all intellectual activities which look at the world through the lens of a standard analysis in terms of either simplicity or complexity. But complexity is ill-defined, as shown by the existence of at least 7 definitions of complexity. Here are the 7 definitions of complexity. Next. Definition number 1. Complexity is a property of a system of systems that are somewhere in between a completely random and a completely regular state, often described by a highly nonlinear set of equations, but sometimes not describable by equations at all. This is a result of definition number 1 coming from a group of specialists. Next one. Definition number 2, due to Gerardo Stuff, who is the man who demonstrated the renormalizability of the standard model. Bad ones, chaos, the need of lengthy calculations, the need for many distinct variables. These are the bad ones. Better one, unexpected difficulty when attempting to describe something in a precisely formulated theory. Point number 5, what is left over after all systematic approaches failed. But Gerardo Stuff thinks also that it could be that complexity is an excuse for sloppy thinking. Definition number 3, due to Richard Kenway, a great specialist in quantum chromodynamics. The complexity of a theory, which means of a problem, is the minimum amount of computer time and storage required to simulate, which means to solve, because if you know how to simulate, you really solve the problem, to a specified, Now, go back to a specified level of precision. Definition number 4, due to Costantino Zales, if we admit that biological and linguistic evolution or financial dynamics are complex phenomena, then their typical dynamics is somehow between strong chaos, which means positive Lyapunov exponent, and simple orbits, which means negative Lyapunov exponents. In other words, complexity, at least some form of it, is deeply related to the edge of chaos, which means vanishing Lyapunov exponent. Since the edge of chaos appears to be related paradigmatically to an entropy index Q different from unity, there must be some deep connection, Costantino Zales says, between complexity and generalized entropy such as SQ. So Zales relates complexity to entropy. Definition number 5, and this to Leonard Susskind, one of the greatest world experts in string theory, the man who discovered the landscape. From the mathematical point of view, a problem can be polynomial, which means that is not too hard to predict surprises. A problem can be non-polynomial or NP-complete, which means different degrees of difficulty in predicting surprises. What means surprises? Surprise means UEEC event, which is unexpected event with enormous consequence, as we will see later. The degree of difficulty can be associated with the level of complexity. Definition number 6. A system is complex when it is no longer useful to describe it in terms of its fundamental constituents. Definition number 7. The simplest definition of complexity is the opposite of simplicity. This is why we have studied the Platonic grand unification, and this is in addendum number 1, and its extension to the Platonic superworld, and this is in addendum number 3, which I have, of course, no time to discuss, but those interested can read my paper. These 7 definitions of complexity must be compared with the world of our knowledge as described in addendum number 3, in order to focus our attention on the key features needed to study our real world. Point number 3, complexity exists at all scales. Next. The logic of nature allows the existence of a large variety of structures with their regularities and laws which appear to be independent from the basic constituents and fundamental laws of nature which govern their interactions. But without these laws, it would be impossible to have the real world which is in front of us and of which we are part of. A series of complex systems is shown in the following figure. I don't know if this is readable, but let me point out some specific features. Example of social complex systems are indicated there. I have just chosen something like few examples. As it is in this figure, we go from traffic flux to the internet network, to earthquakes and seismicity, to social and economic systems, to the behavior of financial markets, to the study of cosmological structures, and so on, including, for example, nuclear physics. A recent study proves that complexity exists at the fundamental level of our knowledge, which means in science. Next. Next. Since the queen of all science is physics, according to Enrico Fermi, we will discuss the great achievement of the most advanced frontier in physics, in order to prove that complexity exists at the fundamental level of our knowledge. Since history is granted to be the best example of complexity, the conclusion is that complexity exists at all scales, as illustrated in the next figure. In this figure, we see in the horizontal axis the complexity axis. In the low degree of complexity, we have science. In the high degree of complexity, we have history. And in the middle, we have all possible complex systems, a group of which has been shown in the previous case. Go on. Next. La próxima. In this figure, we have science and history at the two extreme limits of complexity. Science is the lowest limit in degree of complexity, While history is the highest degree of complexity, the real world consists of systems with different degree of complexity, a sample of which I have presented previously. Next. The degree of complexity of the sample shown in Figure 1 is reported in Figure 2 as being between science and history. This enormous variety of real structures has in common the same experimental evidence for the property called complexity. Next. Now here's a very crucial point. What is the experimental evidence for the existence of complexity with this enormous number of systems? The incredible point is that all these systems have the same experimental evidence. The number of experimental evidence for complexity are two. The AFB, which means Anderson, Feynman, Beethoven type phenomena, which means phenomena whose laws and regularities ignore the existence of the fundamental laws of nature from which they originate. Why Anderson? Because Anderson, in 1972, published a one-page long paper which brought him to the Nobel Prize. Why Feynman? Because Feynman told me in 1972 at Fermilab, in the World Conference of High Energy Physics, that we should study this. And I said, look, I'm engaged in another very big project. We will do this. But as you know, once you say something to a friend, then everyone is strongly engaged in other problems. I just did nothing. Why Beethoven? Because then later I decided that this should be understood to everybody. What means AFB? Beethoven can compose masterpieces of music, this is out of question, but he knows nothing of the laws of acoustics. Nevertheless, without the laws of acoustics, masterpiece of music could not exist. So this is the example of AFB phenomenology. What about Sarajevo type effects? This is due to my friends, historians. They have extracted the UEEC events, which means unexpected events of quasi-irrelevant magnitude, which produce enormous consequences. For example, in Sarajevo, a man has been killed. But how many people are killed in the world? It's this totally irrelevant event. Nevertheless, from this event, unexpected, the First World War started, and according to historians, also the Second World War. So AFB and UEC are the two experimental evidences for the existence of complexity. So the enormous amount of phenomena which have been mentioned by Mitterstrass reduced to two and only two experimental evidences. Next. The only certainty about complexity is the existence of these two experimentally observable effects. Let us now discuss the AFB and UEC cases. Next. A. Anderson, Feynman, Beethoven phenomenon from Beethoven to the superworld. As I said before, Beethoven could compose superb masterpieces of music without any knowledge of the laws governing acoustic phenomena. But these masterpieces could not exist if the laws of acoustics were not there. Next. The living cell and quantum electrodynamics. To study the mechanism governing a living cell, we do not need to know the laws of electromagnetic phenomena whose advanced formulation is quantum electrodynamics, QED. All mechanisms needed for life are, to a great extent, examples of electromagnetic processes. And this means that if quantum electrodynamics was not there, life could not exist. Next. Nuclear physics and quantum chromodynamics. Proton and neutrons interactions appear as if a fundamental force of nature is at work, the nuclear force, with its rules and regularities. These interactions ignore that protons and neutrons are made with quarks and gluons. Nuclear physics does not appear to care about the existence of quantum chromodynamics, the fundamental force acting between quarks and gluons at the heart of the subnuclear world. Nuclear physics ignores quantum chromodynamics, but all phenomena occurring in nuclear physics have their roots in the interactions of quarks and gluons. In other words, protons and neutrons behave like Beethoven. They interact and build up nuclear physics without knowing the laws governing quantum chromodynamics. The most recent example of Anderson, Feynman, Beethoven phenomena is the world could apparently not care less about the existence of the superworld. Nevertheless, we could not be there without the superworld. Now let me move to the unexpected events with enormous consequences from Galilei to present day, which is standard model and beyond. SMNB means standard model and beyond. In figure 3, which is next, is a sequence of UEC events from Galilei to Fermi-Dirac and strange particles. I have no time to illustrate this incredible series of events, all totally unexpected, including superconductivity. I have selected a certain number of events, starting with Galileo Galilei, who discovered that force is proportional to g, which is the acceleration by gravity. During 2,000 years, not 2 years or 2 seconds, 2,000 years, everybody was convinced that force was m times v, times velocity, was depending on velocity. Why? Because no one had ever made an experiment. Then Newton discovered that the force among any object dotated with mass m1 and m2, the Newtonian force acts between anything which possesses mass, is proportional to the product of the mass over the r square. And why Newton invented this r square dependence, according to some historians? Because of light, but let us not discuss this. In this sequence of events, we go to the last one, which is the discovery of strange particles, which have been done in the Blackett lab, which had the great chance of being a pupil of Professor Blackett. The strange particles, why they are called strange? Not because of what you read in books, they explain to you, simply because no one expected these particles. They were discovered in 1947, and no one had the faintest idea what these strange particles were and why they existed. So from Galilei to the strange particles, I have selected a series of totally unexpected events, UEEC events. Somebody could tell me, but this is history. What about new life? Okay, next point. The series of UEEC events goes on from strange particles to the construction of the standard model. I've seen this during my life. I'm coming, as you know, from CERN, which is the European Center for Nuclear Research. Why is called nuclear? Because our father, the founders of CERN, did not know that nuclear physics is not a fundamental law of nature. The fundamental law governing nuclear physics is quantum chromodynamics. This nobody knew. It took 75 years to be discovered. And this is the synthesis of the discovery, which I have no time to explain to you, but those interested can read my paper. Next one. These are details of the electroweak forces, another very big, important point in this development. And next one is the detail of quantum chromodynamics with all the unexpected events, examples of impressive series of totally unexpected events. Next. In figure 7, which is the last figure in this selection, is the most recent synthesis of UEEC events in what is now called the standard model beyond, which is the frontier of physics. Next. I have no time to explain this. I'm sorry you cannot see it, but if you could read the point number 5. In this point, there is the famous God particle. All media have pointed out recently the discovery of the so-called God particle. What is the origin of this? The origin of this, which has been discussed here, as Chancellor Marcello Sanchez Rondo pointed out during our meeting of in subnuclear physics. This is due to the introduction of imaginary masses in description of nature. Question, had anybody imagined this? No one. This was introduced because we were in the middle of great confusion. And my colleague and friend, Peter Higgs, had the right idea at the right moment. Sometimes right ideas considered irrelevant because it is apparently very simple. But the simpler is an idea which nobody has ever had. The most important is because why nobody had ever thought of the imaginary masses, which are fundamental constituent of our logic now. So, next. In figures 4, 5, next one. All this is described in my book, Subnuclear Physics. It is not an accident that the first school in subnuclear physics was founded in Geneva in 1962, when a lot of people were considering subnuclear physics simply a non-existing phenomenology. Now it is at the center of modern physics. And all details of what I've been talking can be found in this volume. Go on. In the same volume, I discussed the standard model beyond, which is the greatest synthesis of all times in the study of the fundamental phenomena governing the universe in all its structures. Next. The basic achievements of the standard model and beyond have been obtained via UEEC events. Moreover, the standard model beyond could not care less about the existence of Platonic simplicity. An example of Platonic simplicity is the Platonic grand unification, which I've mentioned is in addendum 1, and the extension to the Platonic superworld. Next. We see how many times the Platonic simplicity is violated in the unification of all fundamental forces and in the construction of the superworld. Next. The conclusion is that complexity exists at the fundamental level. In fact, starting from Platonic simplicity, the standard model and beyond needs a series of ad hoc inputs in order to be as it has to be. Now let us move to the asymptotic limits, history and science. A key feature in our search to understand complexity is to compare the two asymptotic limits, which characterize the world where we live and which we are part of, which means history and science. Next. The real world seems to be characterized by two basic features, as Mittelschatz has pointed out in his introductory lecture, which are one on the opposite side of the other, namely simplicity and complexity. Next one. It is generally accepted that simplicity is the outcome of reductionism, while complexity is the outcome of holism. Next. The most celebrated example of simplicity, as you know, is science, while the most celebrated example of complexity is history. Talking about asymptotic limits, the general trend is to consider history as the asymptotic limit of two things, holism and complexity, while science is considered the asymptotic limit of reductionism and simplicity, as illustrated in figure 8, which is the next one. On the right side, you see rigorous logic giving mathematics, prediction, reductionism, simplicity, science. On the left, we have the whole of our knowledge, which we have no time to discuss, but it is in addendum 3 of my paper, which needs holism, complexity, and history. There is no question that the two limits, asymptotic limits of our existence, are history on the extreme complexity range and science on the opposite side. Next one. The logic of nature allows the existence of science, which is, I repeat, the asymptotic limit of simplicity, and of history, which is the asymptotic limit of complexity, which share a property common to both of them. It is interesting to define science and history in terms of these common properties, probably the only one which they share, namely evolution. Next. In table 1, we compare these two supposedly asymptotic limits, history and science, on the basis of what historians have called what if, a condition elaborated by the specialist historians in what is now known as visual history. They have invented the visual history in order to compare visual history with visual physics. Now, this is unreadable, but let me say in words what is in this table. In this table, on the left, you have visual history, namely history, life, present day status of the world would not be as it is. For example, if Hitler would not have been born, or Stalin, or Julius Caesar, and so on. What would have happened if in 1905 what went on Siberia would have been in the middle of Europe? No World War #1, because people would have realized that we have to defend this planet from external bodies. And this took about 50 years to be understood. On the right, you have what if in science. There's no question that the evolution of our understanding in the real world, which is science, compared to the evolution of our life, which is history, have completely different behavior. In other words, no matter what is discovered in science, sooner or later, somebody would have discovered what has been discovered. Starting from Galilei up to the present day, what has been discovered would have not changed a world in the scientific understanding of the scientific rules and regulation. Next. Prossima. Whoop. What happens? On the basis of what if, the historians conclude that the world would not be as it is if one or few or any number what if had not been as history tells us. This is not the case for science. Next. Prossima. The world would have exactly the same laws and regularities whether Galileo Galilei or somebody else had discovered that the force is proportional to acceleration, not to velocity. And so on for all other scientific discoveries. Next. It is in the consequences of what if that the two asymptotic limits of simplicity and complexity seem to diverge, despite the fact that the sequence of what if in science belong to the totally unexpected events UEEC, exactly like the others listed in the columns of history. Now let me say a few words on another important point, predictions. How complexity compares with predictions. Next. It is necessary to establish the relation which exists between complexity and predictions. In the previous chapters, we have discussed the experimental basis for the existence of complexity, which are AFB and UEC events. Next. We will now discuss the experimental evidence for the existence of predictions and the sequence which correlates UEC and predictions. We will see that prediction depends on UEC. The experimental evidences for the existence of predictions are the very many results of scientific reproducible experiments. Quantum electrodynamics is the best example. The most famous case is the anomalous magnetic moment of the electron, which is theoretically computed at an incredible level of precision, few parts in 10 billion parts for the electrons. And these predictions are experimentally verified to be correct. Next. Could the anomalous magnetic moment, called G-2 of the electron or of the muon, be theoretically predicted before the discovery of the Maxwell equations and the existence of quantum electrodynamics? No. Next. The sequence which correlates UEC event prediction is very clear. Prediction at the fundamental level of scientific knowledge depends on UEEC events. Next. For example, it is discovery of the laws governing electric, magnetic, and optical phenomena, all totally unpredicted, which produce the mathematical structure called quantum electrodynamics. Next. The mathematical structure was not discovered before the innumerable series of UEC events found in electricity, magnetism, and optics. This series of events...
Could you please round up, because we are getting short in time.
Sorry?
We should come to some conclusion, because we are short in time.
Okay, let us go to the conclusion. Let us move to the conclusions. Our chairman said that we should go to the conclusion. The conclusion is on page, please go to 102, page 102. Is a graphic, a synthesis. Okay. The present status of science is illustrated in this figure. The present status is the discovery of holism. People forget that during 2,000 years, our ancestors have been suffering the illusion that in order to understand nature, they needed to understand everything, until science was discovered by Galilei 400 years ago, which means let us try to solve one problem at a time. This is the reductionistic approach. Now, the present status is, could science be NP complete? If science is NP complete, then we do not know where to go. But I'm convinced that science is not NP complete. I have no time to convince you of this, so I move to the last question, point 10, page 118. The final question. Now, I conclude with the final question. The final question is, why the greatest achievements of science have always been generated by UEEC, which means totally unexpected events? I do not give an answer to this question, and this is my conclusion. Thank you. No, the final question.
Well, thank you. I'm sorry I had to intervene because we should try to follow more or less our program. However, I like to give you the chance to answer to just 2 or maximum 3 questions if there are.